So I'm going here to talk about quantum state engineering, also known as quantum steering, and I will try to connect it with interaction-free measurement, and I appreciate all your comments or protests. This is a list of my recent collaborators, main collaborators on this issue, but I'm particularly proud to have collaborated and to be collaborating with this list of experimentalists. One of them is sitting here, trying to implement some of these ideas on different platforms, including superconducting qubits, cold ions, and quantum optics. And this is a selected part of some of the publications that came out over the past 3.5 years on these topics for my group. Okay, so I'm talking about quantum measurement, and let me first contrast it with classical measurement. So in classical measurement, we may or may not have a back action on the system. Two examples. I'm standing at the side of a highway, taking the speed of cars passing by, and the driver of the car would not sense that he or she are being measured until they get by mail ticket for speeding. As an opposite example, a friend comes to me and says, "Hey, Yuval, I think that I have some gas leakage from my car. Can you make a classical measurement and tell me whether this is the case?" And I say, "Of course, no problem." I approach the car, take my matchbox, light the match, and if the car goes up in flames, I know that there will be a gas leakage. By contrast, quantum measurement must result in a back action on the system. And let me demonstrate it with a simple example. So the simple example is the following. Here I have a double quantum dot, two small puddles of conducting matter collected by tunneling bridge, and I put one electron on this system. By the way, this experiment has been done, and even generalization thereof can be done. This is my detector. The detector is called in the jargon quantum point contact. This is a conductor with a constriction. I inject a current from here. Some of the electrons will be reflected, some will be transmitted, and I'm measuring over the time of the measurement delta T, what is the total charge that has been transmitted. This is the probability distribution for the total charge Q as a function of Q. And the distribution turns out to be double peaked. Depending on whether the electron is on the right or on the left, I will get this peak or the other. And the reason why I have these two peaks is that when the electron is on the left or on the right, the potential of this constriction will be different because of electrostatics. So a different fraction of the electrons will be able to go through this detector. The fact that this distribution has some width is due to the stochasticity of the quantum mechanics. So if you tell me that in a given experiment you measure this value of Q, I know for sure that the electron was here on the left-hand side. Let me take a caricature of this simple experiment. But before I do that, let me take this detector further away from this from the system. So the sensitivity of this detector is reduced. The distribution is still double peaked, but the two peaks coincide with each other. So again, depending on whether the electron is on the left or on the right, I will measure this peak or the other. But if I measure this value of the charge, I don't know for sure whether it belongs with the system being on the left or on the right. I can only say that probabilistically, it is more likely that the system was in the state left, that the electron was on the left quantum dot than on the right, but I cannot tell it for sure, and this is the essence of weak measurement. It gives us a partial or blurred information about the state of the system. So here is my caricature of this. This is my the electron performs radio oscillations and is with equal probability on the left and on the right. I put here my detector, and in this caricature, I inject only a single electron. And now I arrange the system such that if the system is in the state right, the electron for sure will be reflected. And if the system is in the state left, the electron with probability 1 will be transmitted. So now I can draw a 2x2 table connecting the state of the system with the scattering state of the detector. So if the system is in the state right, the resulting state of the detector will be a reflected wave. And if the system is in the state left, the resulting state will be phi1 transmitted. So following a measurement, following a dynamics where I injected an electron and the electron decides what it wants to do, the state of the universe, the system and the detector, can be written as a sum of these two products. Chi naught, external product, phi naught plus chi1, phi1, where chi naught and chi1 are defined here, and phi naught and phi1 are defined here. So this is clearly an entangled and actually perfectly entangled state. If you tell me that the electron was reflected, I know for sure that the system was in the state chi naught. And this is because the two states of the system, phi naught and phi1, reflection and translation, are orthogonal states. So as a result of the measurement, when I looked at the detector and realized that the state of the detector was electron being reflected, the initial state, which was a superposition of left and right, was projected onto the state right. So weak measurement will imply weak entanglement. And coming back to my caricature, if the electron is in the state right, and I send here an electron in the detector, the scattering state will comprise a component, reflected component of amplitude R, and a transmitted component of amplitude T. And now, if the system is in the state left, these amplitudes will change by a little bit. Instead of T, we'll have here T plus delta T. Instead of R, we'll have R plus delta R. So my 2x2 table will now read, if the system is in the state right, the electron, the scattering state of the detector will be amplitude R times reflected wave plus amplitude T times transmitted wave. And if the electron is in the state left, the scattering state of the detector, the dial of the detector, if you will, shows the reflected wave with amplitude R plus delta R plus transmitted wave with amplitude T plus delta T. And I can still write the state of the universe, system and detector here, as a sum of chi naught times phi naught plus chi1 times phi1. But the entanglement will not be perfect entanglement, and this is because the two states of the detector, phi naught and phi1, are not orthogonal anymore. So this as I said, was the state of the universe, following the interaction of the detector with the system. And now, if I project the system into the state electron is reflected, I will end up with the system being in a sole position of this guy, which is reflected, plus this guy, which is reflected, R times chi naught plus R plus delta R chi 1. So the state, initial state of the system, which was a superposition with equal probabilities of left and right, will now become an unequal superposition of left and right, R times right plus R plus delta R times left. So the weak measurement changed the state of the system a little bit, by a little bit. So what did we learn about quantum measurements so far? From this example, you can understand that the quantum measurement consists of 3 steps. The first step, we couple the system and detector to some Hamiltonian, system detector Hamiltonian, and let them evolve in a unitary manner. If the coupling between the system and the detector is weak, we obtain weak measurement. If it's a strong, this is a strong measurement. And following this evolution, the system detector become either weakly or strongly entangled. Second step, after time delta t, this is the time of the measurement, we decouple the system and the detector. And the third step is the readout. Once they are decoupled, we project the detector in a certain desired state. In that example, we projected it onto transmitted or reflected, we read it out, and with this readout, we have a back action on the system. So this looks like bad news, because ideally we would like a quantum measurement or measurement in general to provide us with as much information on the system as possible without influencing without affecting the system. And here I'm telling you that necessarily when we measure the system, we give rise to a back action. So the question is whether we can make this bad news good news, whether we can harness this back action into something good. And the something good is that we can manipulate the system at will. If we perform a measurement in a thoughtful way and repeat those measurements, we can try to take an initial state of the system, which is any state, and nudge the system, steer the system towards a pre-designated desired target state. And this is the essence of quantum steering. But before talking about that, let me ask the question, why do we need at all quantum steering in order to prepare a system in a desired state? We have other means of design. Suppose, for example, that my system is spin half, pointing in some arbitrary direction on the velocity steering. And we want to steer this spin in the direction of the North Pole. And one thing we can do, we can take this spin and project it onto the sigma z direction. And by this projection, we can end up with the spin pointing in the direction of the North Pole. However, it may happen that the result of this projection will bring us to spin pointing in the opposite direction, the South Pole. So success here is probabilistic. We are not certain that we succeed. So projection is not good. The other option to engineer a system in a given state is through cooling thermal contact. I mean, we take this thing, we have a magnetic field in the z direction, such that the spin pointing in the direction of the North Pole is a ground state. And now we take the system and we couple it very carefully and very weakly to a heat bus. And this heat bus is at 0 temperature. So if we are patient and we can wait very long time, eventually heat will go up from our system of spin, which is not in the ground state, to the reservoir. And the system will be cooled all the way to the ground state, which is the spin pointing in the North Pole. Again, this looks good, but it's actually very problematic because if we go to a more complex system made up of many degrees of freedom, many body system, the gap between the ground state and the excited states becomes increasingly small. And in order to be able, when with the successful cooling to the ground state, we need to prepare the reservoir at unphysically low temperature, which is beyond our means. And the last possibility, I mean, we have this spin pointing in this direction. I can apply a magnetic field perpendicular to this spin. The spin will start rotating, and when it reaches the North Pole, I stop. And here I am. The problem with this is that I will, first of all, need very precise knowledge of my initial state. Second, I will need a very precise control of the strength and the duration at which I apply this field. If I'm wrong, then I will end up in another state. So here is my very greedy wish list of what I want to have when I'm talking about preparing the system in a desired target state. I would like to steer the system towards the desired target state. I would like to be able to start with an arbitrary, unknown to me, initial state. I would like the protocol to be robust against some perturbations. I went to the lab, I inadvertently kicked the equipment. I would like still the system to be to successfully overcome this difficulty. I don't want to have a very precise control of the time of operation. And lastly, the target state, my pre-designated state, needs not be a ground state of a Hamiltonian known to me. And with this very greedy list of requirements, I'm coming to a quantum steering. So here are the principles of quantum steering. I have the degree or the degrees of freedom of the system. There can be many degrees of freedom. And I have detectors. The detectors are simple. For example, a spin half detector. And as I told you, I perform many measurements, a very long sequence of measurements. Before each measurement, I reinitialize my detector in a given initial state, which is independent of the running state of the system. It's always, I always say, reinitialize my detector in a given state. Then I couple the system and the detector, let them evolve in a unitary evolution, and then I decouple the system and detector. So here we see, I denote, since it's the state of my system can be pure, can be mixed, I represent the state of the system by a density matrix. So this is the density matrix after the measurement, the time t plus delta t. And this is the state of the universe before I started the measurement. So it's a product state of this running state of the system times the reinitial detector. And these are evolved according to the system, according to the system the detector, according to the system detector Hamiltonian. And now the question is, what I do after I decouple the system from the detector. And here I have several options. One option is that I take the detector, I don't even look at it. I throw it to the garbage, and for the next step, I take a brand new detector, reinitialize it, and continue with that. And in mathematical terms, what I do, I trace out the detector. So I will call it a blind steering because I don't even look at the detector. And the idea is that I'm going to try to engineer a state without, measuring the system, but not looking at the detector. As I said, blind steering is an instance of passive steering. By passive, I mean that I decided on the sequence of my measurements, regardless of what the running state of the system is. So this is one paradigm for quantum steering. And there are two other paradigms which turn out to be much smarter. The other paradigm is post-selective steering. I measure the system, I look at the detector, and then I measure it again, look at the detector, and so on and so forth. And if my sequence of measurements conform to a predetermined sequence that I had in mind, I continue with my experiment. If the sequence of readouts does not conform to that, I close I shut down my lab, I take a 1-year vacation, come back and start it over. And the second, which is probably the smartest, is active feedback steering. I perform measurement, or perform many measurements. I keep track of the history. And depending on the history, I decide what kind of measurement I do next in order to reach my target state at the fastest and the best way. I'm not going to discuss it today, but this is the most, in my opinion, the most exciting direction. We have done some work on that. So let me go back to my stupid and passive blind steering, and I'm going to give you a few examples how to do it. So the first example has to do with a system which is spin half, pointing in whatever direction. I want to steer it in the direction of the North Pole. And my detector is also spin half. And I assume that I can, at each step of the measurement, I can prepare my detector in the direction of up. So you can immediately attack me and say, look, smart guy, you want to have a spin and steer it in the direction of the North Pole, but you assume that at each step you have detectors which are already being prepared in the direction of the North Pole. So what are you doing? My answer to that is that this is indeed a completely stupid example, but in a more important, relevant examples, the system will be very complex, very complicated, and you will see it momentarily. And the detector is simple. So I assume that I can control the state of the detector, but I cannot immediately control the state of the system. But let us say for a moment, just for pedagogical reason, stick with this stupid example. So I have detectors. At each step, I prepare the detector in a state of spin up, and I would like to couple the system with this detector, decouple, trace out the detector, and do it again and again and again, and see how the system evolves towards its final state. So the state of the system is an arbitrary state. The state of the detector is taken to be up, and I have a system detector Hamiltonian, which defines the unitary evolution. It's exponential of minus I delta t H system detector. Delta t is the time of the delta t is the time of the measure. So as a result, the state of the universe following a measurement will be this unitary operator acting on the product state of the system times the detector, which is prepared in the up state. So specifically for my purposes of preparing the system in the state up, I will choose the system detector Hamiltonian, which can be written like that, or more conveniently, in terms of raising and lowering operators of the detector in the system in this way. So sigma s is the raising operator of the system spin, and sigma d minus is the lowering operator on the spin of the detector. So this is a legitimate Hamiltonian. This is the Hermitian Hamiltonian. Now I apply my unitary evolution on this system detector, and what you can see is that the state of the universe, initial state of the universe, was the running state of the system times the state of the detector. The running state of the system times the detector in the up direction. So clearly what you can see is that this guy acting on the system will give us 0, because if we apply the raising operator on the detector, which is already in the state up, it gives us 0. So only this state, only this term of the Hamiltonian will be active. So we essentially cross out this term, and we are left with this one, which gives our process directionality. So this is the first principle of steering. By each time preparing the detector in some state, we gives this dynamics directionality. The directionality is to lead us, take us towards the desired state. Now comes the relation with the Elitzur-Weidman interaction-free measurement, and Avshalom and Lev. Please note and please jump at me, either now or later. So, okay. So again, this is my unitary evolution. This is the state of the universe system detector following this one step of measurement. So now I write more specifically the Hamiltonian, the system detector Hamiltonian, and the state of the system. So the state of the system, when the spin points in some direction, is a superposition of a spin up and spin down with the amplitudes alpha and beta. The state of the detector is up, and the Hamiltonian, which I wrote before, is sigma d minus sigma s plus sigma d plus sigma s minus. More conveniently, I will write this state as this will be up system up detector, this will be down system down detector, so it's alpha up up plus beta down up. So let me take this. I mean, I can easily calculate the evolution to all orders, but in order to demonstrate my point, let me expand this evolution to second order in the small parameter J times delta T. J is the coupling strength of the Hamiltonian, and delta T is the time of the measurement, and the dimensionless number is J times delta T, which I assume is much smaller than 1. So I expand it to a second order, and now I marked the 0th order in black, first order in red, second order in blue, and these act on the running state of the system, which is this guy. So the result of that, it's a 5-minute algebra, will be what is written here. Again, the black parts, the alpha plus beta times 1, are the parts that come from the zeroth order. The red part is the first order, and the blue part is what comes from second order. Now, these two terms are terms where the original state of the detector did not click. Here, this first order, the detector did click. So, in the language of Elitzur and Weidman, this term here is the bomb, is the explosion of the bomb. Or in other words, this is the interaction, the result of the interaction-free measurement. And what I do here, I divide this interaction-free measurement, the state of the detector did not change, into two parts, the black part and the blue part. The black part is just what came out from the zeroth order. The blue part is what came out from the second order, and I call it virtual IFM. Why virtual IFM? Because if you follow the algebra, this came as a result of second order. So actually, during this very short time of measurement, what happened is that virtually the detector clicked and then unclicked. But our time resolution is so short that we couldn't even felt it. But it clicked and unclicked, resulting in the original state of the detector. And this one has clicked. So this would be the detector clicked or the bomb exploded. What I can do now is I can compare the Elitzur-Weidman effect to what I'm telling you about a passive or blind quantum steering. And it goes like that. This is the Elitzur-Weidman. You keep only those states. You throw away the state where the detector clicked. This is a pure state. This is a pure state. With the blind steering, we keep everything, including the state where the detector clicked, and then we trace out the detector. So by tracing out the detector, obtaining a partial density matrix, we'll have a reduced density matrix of the system, which is in a mixed state. The density matrix of the system following the tracing out of the detector will comprise two parts. This is the first part, which is also the density matrix of the Elitzur-Weidman procedure. This represents a pure state, but to this we add the contribution to the density matrix following the bomb, and the sum of this gives us a mixed state. So you can think that when I'm keeping the bomb, the clip of the detector in my procedure, this is bad news because I started with the pure state of the system, and after one step, I obtain a mixed state, which is not something that I would like to do. The good news here is that in fact, I start with a pure state, I will go to a mixed state, and as I repeat these measurements, the the degree of purity will deteriorate. But at some point, and I will show it to you momentarily, this process is reversed and the system becomes purer and purer until I reach the target state, which is a pure state. And you will see it. So this is my comparison between the Elitzur-Weidman and blind steering. In both cases, you have directionality. In both cases, you include, and actually you must include, this term which I call virtual IFM. Now, in the Elitzur-Weidman, the purity after one step is there, it's pure. In blind steering, there is no purity. But now, in the blind steering, I extend it to many repeated steps. And as a result, following a multi-step procedure, I will obtain a full purification. So here is my example of spin one. The state of spin one, the density matrix or reduced density matrix of the spin, is parameterized this way. This is a unit matrix. This is the sum of Pauli matrices. Each one comes with its own coefficient. S is a 3-vector. It's a coefficient of sigma x, sigma y, and sigma z. So here I start with this state in this parameterization. This is the pure state with different components of different Pauli matrices. But you can see that after about 120 steps of repeated measurements, I am left only with the coefficient of sigma z, coefficient +1. This is the pure state of spin pointing in the direction of the North Pole. Here, I start with a mixed state, again, different components of the spins. And nevertheless, I end up with a pure state, which is a spin pointing out, the system spin pointing up in the direction of the North Pole. So let me go to a slightly more complicated example. My system now is two spins, which are connected in whatever direction, connected to my detector, which is the red spin. So my detector is always prepared in the state up. And since I'm talking about two spins, the Hilbert space of two spins can be spanned by 4 states: singlet, triplet plus, triplet 0, triplet minus. And my idea is that I want to steer this, whatever initial state of the two spins is, I would like to steer them towards a singlet. So I need to define my my system detector operators, and here I define 3 of them. This one will nudge any component in the triplet plus to the singlet. This will nudge components in the triplet 0 to the singlet. This will nudge components of the triplet minus to the singlet. And I need to apply them alternatingly. This is the full-fledged form of this system detector Hamiltonians. I will need to apply them alternatingly, and you can see that here I started with whatever components of the triplet and singlet, but eventually after an order of 120, 150 steps, I'm coming to a singlet only. This is the 4x4 reduced density matrix of the system. This is my initial state, and you can see that eventually I will end up with a pure state, which is the singlet state of this density matrix. This looks a bit complicated because I need 3 different types of measurements, but I can make it a single type of measurement. And the inspiration to that comes from a James Bond movie. And in You Only Live Twice, James Bond is served a martini of his liking, and the waiter says, "That's still not shaken. That was right, wasn't it?" And James Bond answers, "Perfect. which is of course a blunder because James Bond like it shaken, not scared, and not scared shaken. So that was a big scandal at the time about the movie. But the inspiration is that I would like to take a protocol which is steered and shaken, which is the following. I will have only one system detector or Hamiltonian, which takes any component of triplet 0 and nudge it, steer it towards singlet. But in addition, I will have a Hamiltonian that acts within my triplet and keeps rotating it such that, or shaking it such that I will always have some component in the triplet 0, which then leaks into my singlet. And you can see that doing so, again, I start with some stupid, arbitrary, ugly state, and I end up after an order of 100 steps in the purely singlet state. One can, and I will not discuss it today. Yeah.
I just wanted to ask, is there an obvious reason you can't just take the sum of the three partial Hamiltonians you wrote down and apply that as one Hamiltonian? It looked to me like that would do the job on its own.
Instead of doing it,
instead of bothering with the shaking.
Okay, so naively, what you could do, I mean, you could take the sum and then expand it to a first order, and then end up with the sum of them. But the point is that you need to go to higher order, and what I showed, you have to go to second order, and that will give you, if you do it within one measurement, that will give you a product of Hamiltonian 1 and Hamiltonian 2, which spoils the game.
That does spoil it.
Yeah. But again, I mean, this James Bond steering solves the problem. And so we did it with many body systems, which are extremely interesting because they can be a resource for quantum computation, and they can be it can be a laboratory for studying strongly correlated systems. And those of you who know, and we did it for AKLT states, functional quantum Hall, W states. I will not go into details, but you can see that in one of those examples, you start with a purity 1, pure state. The purity, the protocol degrades the purity, but eventually it recovers, and we come to a purity 1, but a different state, which is the target state. You start with some trivial state, and we come to the ground state when the purity goes down and goes up. So the purity going down would mean in the Elixir-Weidman jargon many bombs that were there, but we ignore the bombs. So instead of a summary, what I said, let me highlight two very promising and intriguing directions, which I think are at the core. One is to identify this interaction-free contribution to quantum set engineering, especially on many body platforms. And the other is to identify interaction-free measurement using smart measurements. I mentioned the active decision making, and this is the one work in this direction. And with this, I would like to thank you very much.
Thank you, Yuval. Questions? Paul?
So we had this evolution from pure to mixed and back to pure. Is there, I guess I want to follow it pretty well, but is the issue that there's some larger environment that is preserving the second law so that we don't have going from mixed to pure, 47 was a thermodynamics from the difference.
Are you concerned that the entropy going down?
Well, just inside his evolution, he's going from pure to mixed.
So you're concerned that what Marshall said, you're concerned with the fact that the entropy goes down. Is this?
Yeah, I'm just confirming that the issue, the resolution to that, is that there's other parts of the environment that you're not.
But you're doing that somewhere. I mean, the fact that you couple and decouple the system and the detectors. I mean, let me just say, I agree with you that tracing out the detectors is like introduction of an environment, reservoir. It's an engineered environment, it's a very clever environment, but nevertheless it's environment. When I go to an active decision making, it's not environment because I'm maybe following the trajectory. But even though I engineer my environment, I do some work in coupling and decoupling. And actually, what you are saying is very interesting because this such protocols. I mean, we are exploring this now. Such protocols of steering can be used in order to cool down systems. This is why I sent you my inquiry a few weeks ago. So I think that there is some bridge between what some part of the community is doing and what we are doing.
Just to follow up and clarify, even though I understand you're doing this active switching, so you're doing work, isn't it still just literally true that the entropy of the discarded detectors has gone up so that there's no problem with false original question?
I think so, yeah.
So in that sense, like a spontaneous emission begin in E plus G, and first spontaneous emission will generate a mixed state, but eventually it'll leave you in the ground state. Purity does go back up naturally, but because the electromagnetic environment is so
But I put those parts in the garbage.
exactly.
Okay. I don't care about it.
So Yuval, you mentioned there was this horrible gaffe in the James Bond movie about mixing up the shaken versus the stirred. But I think that there's a horrible gaffe in your slide of in the quantum mechanics, because the Hamiltonian should be the stirring and the measurement should be the shaking.
It's true. Okay. That's in the eyes of the beholder. But at least you understand why I use these terms, because for me shaking was take the undesired sector and do something to it. I mean, the fact that I rotated it, okay, but I could have shaken it, I could have done something chaotic, stochastic to it. The point is that I have one state in this undesired subspace, from which I can withdraw from amplitudes to my desired state, and then everything else I cannot calculate. But thanks for pointing it out. I mean, next time I will be more thankful.
Suppose I start with a system of n spins, and they are mixed completely disordered, and then I want to steer them all to point in the z direction, right? If I can do that, they seem to be violent as well.
The spins talk between themselves or not?
Sorry?
Those spins,
Yeah, they don't interact.
they have something in return. Do they talk between themselves or not?
No, they don't interact. You just have a mixture that corresponds to final temperature, but they're completely mixed. Now you steer all of them to be pointing in the z direction. That's like the entropy of the system. In principle, it's like bias in the cell door, like Maxwell thermal, you say. So why can't you do it in your system?
Why can't they do it?
In your process, for a large number.
No. Look, very well. So I'm talking about a huge number of spins which do not interact with each other, then each spin is on its own. I mean, regardless of what is the initial state, I will repeat my story in single spin for each of the spins in my system, and here I go. I mean, each spin will be separately still for
same.
But I'll give you an example when it's not that simple.
But I want to feel about the freezes. Why don't the violate the cell though? I don't know anything about the spin. They are completely disordered, and I succeed to all of them to the same single state. Why is that not a violation of the cell law?
Because I couple my detector and remove it.
Yeah.
And in doing so, I did some work. I'm not telling you where my energy. You know, I needed to connect something to the to electric power. So.
But in a sense, it's an example of the maximum level. So the question is now, suppose you have a system echoing in a helice, and you like to end up with all of them being in one half of the helice by steering. Can you do this?
Second, suppose
you start with a large system of large number of atoms that are filling a box, and now you do a steering and collect them all into a formula.
Do they interact or not?
Either way.
Okay. If they don't interact, then I'll do a process where each atom separately is moved to that corner of
the question is, the problem is, how do you know to interact each time with individual atoms? If they are indistinguishable.
Okay. I don't know. I never thought about it. I don't know. But to your question about the question about maximum level, I don't think this is the case. I mean, in the same way that I have a home refrigerator, and the temperature in the refrigerator is low, but of course there is heat.
No, it's not the same thing. Here,
but what I'm doing is actually. Okay, let me put it this way. With this stupid mechanism, protocol, the classic protocol, I don't need to have any information on the system or any selected information on the system in order to proceed and eventually succeed.
next result.
Can I have a comment?
You're the chair.
So let's do Lev first, then Ami. It's more like a comment. Maybe it's to compare, to put it in the context. Lucien gave a talk about his paradox. And once I sent an email to Lucien, look, there are all these papers with photons claiming that they did your paradox. This is not your paradox, because with photons, you have only interference. And in your paradox, you have interaction between electron and positron. It's a similar flavor, but it's different. Now we had apparently it also was a Lucien idea, so he was happy. Now I probably should be happy that everything is called EVI effect, and I don't want to talk for E. But for me, it's not VI effect. The VI effect, the crucial point for me, is that the particle was not where was the interaction. And here I didn't hear anything about this locality. Maybe it didn't click, this is for me not interaction-free measurement. The interaction-free measurement that I get some information about the place where I have not been. This is for me the essence of EVI effect. Is it, do you get something
like this in your story?
No, I'm sorry. I mean, first of all, I don't like to argue about semantics. And if you want me next time to remove the V from the EV, I will do this. But the point is that in your thing, the way I see it is that I have a Mach-Zehnder interferometer, and the injected electron can take the upper arm or the lower arm, you don't know which arm or which superposition, and then you perform a measurement on one particular arm. And the question is whether, to me, the important thing is whether the detector clicked or not clicked. But if you tell me that for you, the main thing is that the electron was in two states which were non-local in different points of space, then I will tell you that to me, the question here is whether the system was in two different points in Hilbert space, up or down. I don't see the essential difference between two different points in Hilbert space or two different points in real space. Of course, I understand that there is a difference, but I'm saying that I'm emphasizing this point and not your point.
Okay. For me, IFM it's all about 3D and locality in 3 dimension, and I get information about the bomb here, about shutter, whatever. And I have a reason to say that my photon, my probe was not there.
Okay, so I think you've made your point. I think everyone understands it, and I think everyone understands Yuval's point as well. I think we're out of time, but maybe if you, Avi, we want to have a very short comment.
No, I don't think the point.
All right, let's thank Yuval again.